We've got a dice and we think that the dice doesn't show a 6 often enough. So the data that we're going to get in order to test this claim is we're going to roll the dice 12 times and we're going to count how many 6s we get. And what we need to work out is at the 5% significance level, is there enough evidence to suggest that the number 6 doesn't come up enough? So basically, is the probability of getting a 6 less than a sixth? So the first thing that we're going to do is we're going to define our test statistic. So x is our random variable, which is the data that we're going to get. So we're going to count the number of 6s we get after 12 rolls. So we know that x is going to be binomially distributed, the number of trials is 12, and p is going to be the probability of getting a 6. So next we'll write down what our null hypothesis is. So our null hypothesis would be that the dice is actually fair. So that would be the probability of getting a sixth is a sixth. And our alternative hypothesis is what we're trying to find evidence of. So we're trying to find evidence of the fact that a 6 doesn't come up enough. So that would be the probability of a 6 is going to be less than a sixth. So next we're going to think, well, if H0 is true, i.e. the dice is fair, then x would be binomially distributed, 12 and a sixth. Remember, x is the number of 6s we get. So it's worth noting that we would expect, well, how many 6s would we expect? We'd expect a sixth of 12, which is 2 6s. So if the dice is fair, we would expect 2 6s. So if we were trying to find evidence to support the alternative hypothesis, we would expect x to be small. We'd expect to get less 6s. So here we're going to say small values of x will support the alternative hypothesis. So this means that we're doing a left-tailed test. So the first method that we'll look at how to do this is to use the p-value method. And I'd recommend using the p-value method wherever the question doesn't ask you to find the critical region. So in this question, it's not demanding that you find the critical region, so we'd use the p-value method. So let's draw a little sketch of this distribution just to help us think about it. You don't need to draw a sketch, and I wouldn't expect you to draw a sketch in the exam, but it can help you think about what's going on. So along the horizontal axis, I'm going to put our specific values of x, which is the number of 6s, and remember we're out of 12 dice rolls. So we could have 0 6s, we could have 1 6, we could have 2 6s, and 2 is going to be the most likely. Remember, this is our distribution under H0, i.e. when x follows a binomial distribution, 12 a sixth. So we know that 2 is the most likely outcome. We could have 3 6s, 4 6s, etc., all the way up to 12 6s. But that's going to have a really, really small probability. So what we've got to do is we've got to, and remember on the vertical axis, the height of each bar represents what's the probability of that number of 6s. So because we're doing a left-tailed test and small values of x will support H1, we've got to work out whether where we are is in the left 5% of the distribution. And it's 5% because our significance level is 5%. Well, we rolled the dice and only 1 6 appeared. So that means we're here in the distribution. Okay? So we've got to work out, is this in the left 5% of the distribution? And that'll tell us whether it's in the critical region. So what we're going to do is we're going to work out what's the probability of being where we are or to the left, because it's a left critical region, small values of x. So let's work out the probability of x being less than or equal to 1 under H0. So we'll go to distribution binomial cumulative, and we want the probability of x being less than or equal to 1. The number of trials is 12, because we're rolling the dice 12 times, and the probability, if H0 is true, is a sixth. So we get that it's 38.1%. So that means if H0 is true, then this probability of being at 1 or lower is 38.1%. So that means we're definitely not in the left 5% of the distribution. If we were to draw it on the diagram, 5% is going to be somewhere there maybe. Okay? So we can say, remember this is our p-value. The probability of being where we are or to the left in this case. So because our p-value is greater than the significance level, we are not going to reject H0. We're not in the left 5% of the distribution. So we're not in the critical region. So in this case, it's because 38.1% is greater than 5%. So next we're going to say do not reject H0, because basically we didn't see a small enough value of x. We weren't in the left 5%. So do not reject H0, and then our conclusion in context is going to be there's insufficient evidence to suggest that the probability of getting a sixth is less than a sixth. And the key part of this is we've shown what the p-value is, and we've said that it's greater than 5%. So we're not going to reject H0, and we've got insufficient evidence, and then the conclusion in context. Okay, next let's look at the critical region method. So in this method, we're actually going to work out what is the critical region. So we know the probability of x being less than or equal to 1 is 38.1%. So we can't have less than or equal to 1 as our critical region because the probability of being in the critical region is too big. Okay, so we're going to have to make our critical region smaller. So that probability is 38.1, which is too big. So the only other value that we could try is less than or equal to 0, or basically equal to 0. So the probability of x equaling 0 is 11.2%. And this is actually also too big. So this is a bit of a weird question. We don't actually have a critical region. It's impossible at the 5% level to make a conclusion to be in the critical region, because that's 11.2%. So it's a bit weird thinking about the critical region in this case, because there isn't a critical region. It's impossible to reject H0. You can't get a value of x which is small enough to be in the critical region, because the critical region doesn't exist for this test at the 5% level. So that would mean that no matter what value of x we get, we could just say do not reject H0. And then you would make the same conclusion as before.